Hello. Today we want to review some interesting shaft problems. Yeah, there are two types of a shaft we're going to consider today's class. One is the shaft in parallel connections, and the other one is the shaft in series connections. Okay, I will draw here. Say first, before we consider shaft, I would like to remind you of the bars in parallel or series connections. Okay, here is the bar, and bar can have two bars actually. One bar is like that, and the other one bar is like that with the different cross sections and different lengths. So this one we call series connections. Bar in series connections. So here is the bar 1. Bar 1 and bar 2, and each one has a different length, L1 and L2, and cross sections are also different, and stiffness, Young's modulus is also different. So E1, A1, and here is the E2, A2. Now these two bars in series connected, subject to a force on the right hand side. On the left hand side, it is fixed. This is the bar in series connections. This is a very simple problems, and which we already covered a long time ago, but we're gonna solve again to understand and the analogies between shaft and bars. Okay, here first we need to have a force equilibrium, of course, and this will be a F and F, and here will be F, and here will be another F and F. So they are all F, and here is the E1 and A1. E1, A1, and E2, A2. And this is L1 and L2. Now, what we want to calculate is the delta 1 in the bar 1. So delta 1 is simply given as a E F L1 and E1 and A1. And here delta 2 is given. F L2 So here is the delta 1 and delta 2. And the total displacement, the delta, will be simply delta 1 plus delta 2. And so we put these two terms into here. Then F will be L1, E1, A1 plus L2, E2, A2. So simply F and delta relation is like that. And bar, another case is the bar in parallel connections. This was a bar in series connections. And bar in parallel connection is that so we have two bars. Actually, two bar in parallel connection is not easy to draw, but in mechanics wise, the two bars in parallel connection is the same as like that, and then the force is applied at the junctions. So this is a F, and again this is the bar 1 and this is the bar 2. So in bar 1, we can say that this one subject to a F1, and the bar 2 is subject to a F2, and then there will be certainly a F1 and F2. This is a F1 and F2, and simply F is the F1 plus F2. So due to F1, there will be a extension delta 1. Delta 1 equal F1, L1, and E1 and E2. And delta 2 equal F2, L2, E2, A2. For each one, we have this delta definition. And now the main point here is that delta 1 equal delta 2, and they have a same extension as a delta given here at the force. This is a delta, and delta is the same as the delta 1 and delta 2. So using this force equilibrium and this geometric deformation condition, we can say that F equal, now F1, what is F1 here? F1 is that E1, I'm sorry, this has to be 1, E1, A1, so F equal E1, A1, and I'm trying to have F1 here, F1 here. So F1 E1 A1 over L1 delta 1 plus now F2 E2 A2 L2 delta 2. Now we have a delta 2 and delta 2, delta 1 and delta 2, they are same. So this one will be a E1 A1 and L1 plus E2 A2 and L2 and delta. Okay, so again, this is not an advanced topics, and this is the very classical the fundamental topics which we already covered long time ago at the almost at the very beginning. But I like to remind you of all the process. Then we will move to a shaft. So anyhow, we want to change this format to F equal the E1 A1 plus E2 L2 E2 A2 and delta. This is case of the a beam bar in series connections, and this one is the bar in parallel connections. So very similar to this bar, let's move to a shaft case. Now, the shaft, we have one shaft like that, and second shaft, they are connected in series. So in shaft case, at the end we have a torque applied, and this one is the shaft 1, and this is the shaft 2, and this is the length L1 and L2, and this is the G1 J1, and this is the G2 J2. So this is the shaft in series connections. And now let's have a free body diagram for separate shafts, and obviously we have a torque T and T and T and T here. Since it's the torque, I want to express a double arrow, and then the angle phi, not delta, now is angle T, which rotate with respect to on the left hand side. So phi will be a T L1 and G1 J1. This I will call P1. So this is the angle rotation at this point with respect to here. And then P2 again T L1 G 2 J2, and this is also angle of the on the right hand side with respect to left hand side. So a total phi, okay, total phi on the right hand side here. So phi equal phi1 plus simply phi2, and as you can see here, L1 and sorry, this is a L2. L1 G1 J1 plus L2 G2 J2 and torque T. Okay, so this is the relation between phi and torque which applied. Now the second case, very similar to the bar again. We have a shaft 1 and shaft 2. They are connected at the center at the junction, so we apply the torque T. And then on the right hand side, there is a torque T1 and torque T2. And the right hand side, there is the T1, sorry, T2 and T2. And now, from the equilibrium, the T1, T equal, T applies a T1 plus T2, and the angle P1 is simply same as P2, and which is the a angle rotate at the junction point where we apply the torque T. So from this T1 is simply G1 J1 and L1 and P1, and T2 is G2, there's a J1, G1 J1 and G2 J2 and L2 and P2. But again, this angle are the same. So this will be simply G1 simply G1 J1 and L1 plus G2 J2 and L2 and phi. Okay, so and these are again this is the shaft in series, and the second case this is the shaft in parallel. And if we compare to the previous one, well, as you can see here, they're simply the same. Of course, here we can T equal L1 G1 J1 plus L2 G2 J2, and this is the phi. So same format as the bar case. Okay, so we have identical analogies between the bar and shaft. That is the one point I want to mention. And actually, using this flow chart, so as usual, I'd like to use this analysis flow chart for the shafts in a parallel connections. I will draw here the case, like that, and apply. We talk T here, and main point here is that we have a T1, and on the right hand side we have a T2, and here is the angle Phi1, and here is the angle Phi2. So here, the force we apply is the torque T, and materials we are considering. In this case, we can simply say G1, J1, and G2, J2, and deformation conditions. And deformation condition is that deformation condition is we have a Phi1, but Phi1 and Phi2 they are the same. And the equilibrium condition is the T torque we apply to these two shafts is the T called T1 plus T2. That is the force equilibrium equations. Now, the stiffness and strength, in broad sense, this stiffness is in this case T1, and T1, and the strain is a deformation, so this will be P1. So and T2, and now we have a P2. So T1 is simply there is a stiffness combining T1 and P1, and which is what? Which is a T1 equal G1, J1, and L1 and P1, and T2 equal G2, J2, and L2 and P2. So what I'm trying to emphasize here is that in general sense, in this shaft case, the torque T apply is this is the external force, and the forces are split into T1 and T2, and total sum of the T1 and T2 should be the T. That is the equilibrium equations, and each shaft will have a Phi1 and Phi2. So Phi1 and Phi2, they have a condition that they have to deform together. So it is a deformation condition, and stiffness in this case is a T1 and Phi1 has the relation GJL, and T2 and GJL2. So we solving all the equations as before. That is this case, and or very similar passions, the bar in parallel connections, and the forces are force equilibrium and deformation, force equilibrium and deformation conditions, and this is a stiffness conditions, and so this is the final equation result, F and delta, and this is the stiffness. Very similarly, so combining this, we have T equal G1, J1, and L1 plus G2, J2, and L2, and phi. In the very beginning of this class, actually, we consider as the case as F equal Kx, and as you can see here, this one can be considered as the K, and this is another spring K2. So for example, we have a spring 1 and spring 2 and connect to here, and say when we applied F, and this is a K1 and K2, the result will be exactly same. So again, what I'm trying to say is that using this flow chart, we can solve this statically indeterminate problem. And in here, the meaning of the stress and meaning of strain is a little bit different. Well, in broad sense, they are the same concept. Stress in this case, force, and strain in this case is deformations. And so in global sense, it's actually the same problem and same procedures. And force we apply, and material property, GJ, and the deformation condition, and two shaft has two different angle of twist, but they have to be same. And using that deformation condition and equilibrium condition and stiffness, now combining them all, we have this a torque and twist angle relations, and this procedure can be equally applied to bar as well, and also these procedures can equally apply to a shaft in series. Again, as I mentioned, this is a shaft in series connections, and the second case is this one. This is the shaft in parallel connections. Okay, I hope that you got the idea. And this analogy, which exists in bar and shaft, will be equally applied to a beam case, as I mentioned before. So it is very interesting to pay to notice that these features. Okay, and simply we can extend this case to a more to a number of different. Say we have a multiple shaft in series case, or the number of shafts in shaft in parallel series, parallel connections. So that you can certainly drive yourself. And what I'm saying is that multiple shaft is that we can have this 1 and 2 and 3 and so on. We can, and then at the end we can apply torque T. And now we can say this is a GI, JI, and the length is simply LI. So we can solve this problem. And another one is shaft, and in this case the shaft is parallel. You can consider as a 2, but actually which is the same as I mean similar, not exactly same, but say we can consider as the shaft with the another materials, and another materials, and so on. So this is the case where we apply the torque T, and we have a L and GI and JI. Of course, in this case, the length is L. So we can easily extend the concept to a multiple series connection and multiple parallel connections. And this will be, again, a very interesting problem we should be able to solve. Okay. And I like to make a very special notice which needs to be understood by all students. And the chapters is chapter 8 is about the shaft and torsions, right? And which is the same. And I add few slides here covered today. And now the chapter 9 is about the thin wall shaft. Okay, thin wall shaft. That nothing changed, but we do not cover at this point. Okay, so we move to next chapter. Is chapter 10, beam theory. Now the beam theory is the most important one, and I rearranged chapter 10 and chapter 11. And chapter 11, I changed the topic title to beam theory 2, and this is about the deflection due to bending. And there is a chapter 12. Chapter 12 is the very special issues. Very special issue which needs to be understood regarding beams. And in chapter 12, it covers the singularity function and the second of the moment of inertia and shear stress in unsymmetric, and beam bending of beam with the unsymmetric cross section and shear center. A little bit special sections and which needs to be collected in a separate chapters because these issues are not quite relate to a mainstream of the beam theory. So I collect them in different sections. So that is chapter 12. And then chapter 13 is about a buckling. Okay, buckling is the very advanced topic, but very important topics. And energy method. See, this the first semester we covering very fundamental topics in each structures. So we're not gonna cover the buckling, and we're not gonna cover the energy method, but we gonna cover very importantly the beam theory. Okay, beam theory 1, chapter 10. Again, there were the chapter 9, which was the again is a theory of the shaft, but applied to a thin wall cross sections. And this is a little special sections in the shaft theory, torsion theory, and which we will skip at this point and move to a beam theory. Okay, so tomorrow I will cover the beam theory, and The reason I rearranged this section is that to make a complete analogy between bar, shaft, and beam, so that a student can better understand using those A+1 flow chart. Okay, so tomorrow we have another online class. Okay, so talk to you tomorrow class. Thank you.